before, I mean, first thing I want to do is take questions about any homework problems. Are there any? Yes?
The skin depth homework problem.
All right.
6.26.
So, first of all, I covered skin depth, I remember that, and I put it on. So I'm going to put the definition of skin depth on the board again. It's 1 over the square root of pi f mu sigma. That's the definition of it. Now, what's the actual question?
It asks for DC and AC resistance.
So, for what? What again?
DC and AC resistance over 1 meter.
Here's the question, if you can read it off my hand. 62.25.
Calculate the DC resistance per meter for a 4 millimeter diameter wire. Yeah, all right, we'll do it. This is a really good problem to do.
What number was it?
6.25. 25.
I got it.
All right, let me go through this. First of all, whenever you think about resistance for anything that has a constant cross section, you're talking about along the length. For instance, if we have a circular piece of wire and it has a length L and it has a radius A, it would cause the area here to be pi A squared. And if current is flowing down from one end to the other, and we attach a voltage here, we get a current that flows here, and that means that there's some resistance, which would be V over I by definition, right? Now this is from Emag2. You remember that resistance is proportional to the length. You all remember that, right? So when we talk about resistance in general, we know if we're talking about resistance through something that, or down the pipe, as it says, where the pipe has a constant cross section. It could be rectangular, it could be triangular, it could be cylindrical. As long as the cross section doesn't change, then resistance is going to be the length L divided by sigma, and sigma would be the conductivity in that wire, whatever it may be. And then it's times the area, put that down, that the current flows in. Now, R DC, that means if it's not time varying, would be L over sigma. The area would be pi A squared. Does everybody agree with that? If they wanted a per meter resistance, we would divide by L. It would just be 1 over sigma A. Oh, got me on that, class? Remember, the area is the area the current flows through. Now, if you have something, this is part 2, that's the DC resistance. If the skin depth is less than A, in other words, if the skin depth is less than the radius, then what you have is this. If you look down the pipe of the actual wire, here's radius A, and if we go in 1 skin depth, this would be a skin depth. That means that all the current would actually flow in that skin depth right there. It's going to all flow there. I would be on the surface. Just flowing there. Does everybody understand that? None of that, the electric field, when you have an electric field like this, it's in this direction, but if this is not a DC voltage, if it's a time varying voltage, and you get a skin depth, all it flows this way, but as it's flowing, it's trying to propagate towards the center, it gets shorted out because of the skin depth effect. Are you with me, class? Now what that means is really, it looks like this is really a hollow wire. The current has to, it's only going to flow in the actual area 1 skin depth deep in the wire. That's what it's going to flow through. Got it? So what is that area? Well, the exact definition would be equal to the area of the entire thing, that's pi A squared. That's the entire cross-sectional area, correct? And then you would subtract off the area from here to here in white. And what is that? Well, that would be pi times quantity A minus the skin depth squared, wouldn't it? So it's minus A minus the skin depth squared. I think I did this last time. How many see this right here? You with me? You guys see it over here? Got to make sure everybody sees it. If you think about it, what are you really doing? You're subtracting off all that white area from all the area. So that's whatever remains is going to be where the current flows. Got me? Now pay attention to this part. So when we look at this, we actually get the area is pi. Now I have A squared minus, well then I have minus A squared, right? And I have plus delta squared. but I have minus 2 times a times delta as well. So what I'm left with, the a squareds cancel, and now I have pi times 2 delta a minus delta squared. Do you all see this here? Now here's the thing. Almost always, but not always, almost always. What you get is if and only if delta is much less than a, which is the case 99% of the time when you're dealing with high frequency stuff, then what you get is the area just being equal to 2 pi a times the skin depth. Can everybody follow me on that? So the delta squared goes away because it's so much less than the term right here, the 2 delta a. Follow me? Because a is so much greater. Now, if that's the case, first thing we've got to do for this problem is calculate the skin depth. So what's the frequency of operation, people?
1 gigahertz.
What is it?
1 gigahertz.
All right, so you got 10 to the 9th hertz. This is in copper?
Yes, sir.
All right, so sigma for copper is 5.8 times 10 to the 7th, and the units are 1 over ohm meters or Siemens. All right, now mu for copper is mu naught, is just mu naught. So that means the skin depth, help me out here guys, I need your calculators, square root of pi times 10 to the 9th times mu naught, which is 4 pi times 10 to the minus 7, times sigma, which is 5.8 times 10 to the 7th. What's that going to be? You got to give that to me.
It's 2 times 10 to the negative 6.
Is that correct? I mean, I'm just making sure you got that? So this is 2 times 10 to the minus 6 meters. That's 2 microns, right? Extremely small, 2 microns. You got me on that, everyone? That means when I take a look at the resistance, the AC resistance, do they give us a length that they want it per meter?
No, sir.
Per meter?
It's per meter length.
That means you assume L is 1. It's the easiest way. So the resistance is just 1 over sigma 5.8 times 10 to the 7 times the area, and the area in this case is going to be 2 pi. What's the radius of that wire? What is A?
4 millimeters.
4 millimeters. Wow.
2 millimeters.
Oh, I'm sorry, 2.
Is it 2 millimeters?
Yes, sir, 2 millimeters.
So it's 2 times 10 to the minus 3rd here, and then it's times the skin depth, which is going to be 2 times 10 to the minus 6. Minus 6. So that should be the AC resistance. Could somebody do that? I don't always trust the book. There are wrong answers occasionally. What'd you get for that?
0.66, what I got.
Is that what's in the solutions manual? 0.66? All right, so it's 0.66 ohms per meter. That's how you get the AC resistance. What else do they have for that problem? Any?
That's it.
Is that it? Any questions? Yes, sir.
For the first area formula right there.
Here?
Yes, sir. Could you explain that setup, please?
Sure. What is the area of a circle of radius A?
Pi r squared.
Right, that's pi r squared, right? Or pi a squared, right?
Pi a squared.
All right, now, what's the area of this circle right here of radius b? That would be pi b squared, right?
Yes, sir.
Well, b in this case is just equal to a minus the skin depth, because you go out, but not there all the way to the edge, you go out right to here. And that distance would be a minus the skin depth, that's all it is.
Okay.
Any other questions about that one? Now, what about other questions in general about the homework? Anything? I usually get 1 or 2, but maybe it was, this class is that solid. All right, good.
Could you put the answers in the chart?
What?
Was there a chart?
Oh, yeah, could you go over the one that you gave us that was like, just listed as number 1?
Where I did give you the answers, but I didn't give you the solutions. Is that the one?
You gave us the chart to fill out, and then there weren't answers.
Oh, yeah. Ooh. Yeah, we can do, how about we do it real quick? That'll take care of the problem for me. So please, if you have a calculator, get it out and we can handle this.
We'll check it on that.
You're gonna have to help me. Tell me what's being asked for in this column.
I think it needs, is this one with 3?
Yeah.
Is that your last one? Okay, I got it.
Just read it.
Okay, so region 1, z less than 0, has constitutive properties, epsilon equals 72.
No, epsilon relative 72.
Epsilon relative, I believe.
Yeah. Okay.
Sigma equals 5,000. Mu r equals 1. And electric field E equals 5e negative alpha z
E equals 5e to the minus.
alpha z
Okay.
cosine 2 pi 10 to the 9th t minus beta z. That'll be in the AX direction, millivolts per meter.
Is that incident field?
Sir?
The incident, does it say incident or E sub I?
Electric? Oh, okay.
Never mind, go ahead, I think it's incident, it's probably
I
getting
think
the
it's,
plus direction.
yes, and.
What else?
Well, this is kind of.
This is in the Z
Yeah.
direction, this is X, what else? What about over here, region 2? This is perfect for what I'm
I had a
talking about.
question about that.
It
Because
doesn't
there's an
say.
AX and then there's an AY.
That's because that AY should not be there.
Okay. That's what I was throwing.
I'm sorry about that. That's my bad. I'll get to that. So this is a field in the AX direction. By looking here, we see it's propagated in the plus Z direction. Follow me? You assume beta positive. Agree, class? So now we start. What do they want, by the way? What's in region 2?
It doesn't say.
Doesn't say, it just says region 1 where Z is less than 0, so I
Right?
guess that's.
There's no region 2 to worry about. That's better than. All right. What do they want?
Eta,
Alpha.
alpha, no, they want,
I mean-
the propagation constant.
All right. That's gamma. That's no problem. That's alpha plus J beta. So go ahead.
They want the phase velocity,
V phase. What else?
they want the wavelength,
Lambda. Okay.
they
All right.
want the phasor domain H.
All right, we're gonna get all this in short order. Yes.
What's the direction for E?
E is oriented in the AX direction. That's supposed to be an X. Now, if you can't read, if you can't read my writing, let me know. I'm not sensitive about comments and criticisms. They help me. I know I always wondered why people's handwriting gets worse and worse over time, doctors especially. And I think it's because we don't have much time to do what we need to, so we just scribble faster and faster. And I've flunked in penmanship in grade school now, but that doesn't matter. I know what I'm talking about. Anyway, back to this thing. First thing you're going to do is take a look and find the frequency. What is F and what is omega? Omega is always what? Coefficient of t, isn't it? Inside the cosine, correct? Oh, and can you read my writing? It's 2 pi times 10 to the 9th. Now, what does that make F? Automatically. Class? 10 to the 9th hertz. That's it. So you identify that. Everybody agree with me? All right. Now, the second thing you do, you look at these parameters, and these are straightforward formulas. First, we're going to need this one. I'm going to put the ones we need down generally, and then you'll get the definition. We're going to need eta. So eta is the square root of j omega mu over sigma plus j omega epsilon. Now remember, that epsilon is epsilon naught times epsilon relative, or 72 epsilon naught. Just remember that. The epsilon relative is not the value for epsilon in general. Understand? That's just a weight on how much better that material is at storing energy. That's the first thing we need. We'll get that in a second. Second thing we need is gamma, which is alpha plus j beta. Gamma is equal to the square root of j omega mu times sigma plus j omega epsilon, right? That's what we're going to get. We need that. After that, right, we need phase velocity. Well, phase velocity will always be equal to what? Omega divided by beta. You all recall, I've done these things a couple of times. You've had them in Emag2. These are the things you have to know at the back of your hand. Now, if you don't, and you're a little troubled that you don't worry. You're going to be working a lot of problems, and I'll make an honest effort to do that. This stuff will be burned in your brain. You won't have to worry about it. It'll be like F equal MA or V equals IR. He is sleeping. He's not dead, right? I had a kid in a class years ago. You see, have you ever been around somebody who had an epileptic fit? You know what that? It's so tragic that this happens, and it's sad. Well, a lot of times it's right before they get into that, they faint, I guess. And I had a kid that I called Captain Narcolepsy. I wish I didn't call him. He'd come in to an 8 o'clock class every single morning when I taught. And it was in 3810, so it's not for EEs. And that kid would sit right up front, 5 minutes into the lecture, out cold. I mean, like, see, nudge him, he doesn't get up. He worked all night. And he got in a bad accident, and I never saw the kid again. Apparently he was driving, probably fell asleep like he did in class. And then I heard that sometimes people with diabetes have a diabetic coma, and they act like they're it looks like they're asleep, but they're actually fighting for their life. And that's how come I never see a person like that, especially when I'm lecturing. I always make sure that they're at least awake. You know what I'm talking about, right? I mean, that's a serious problem. People die from diabetic comas, and I hate epileptic fits because you got to stick something in their mouth. All right, that's this, right? We get beta from up here, don't we, guys? And they want wavelength. Now, what's wavelength? Well, technically it's what? 2 pi over beta. That's the best single definition, isn't it, class? That's fundamental. Some people say it's phase velocity over frequency. That's fine, too. But this is the fundamental one. Got it, guys? So let's go about getting them. I put the equation up here. You've got omega. You know mu is just mu naught, right? And, well, make sure everybody knows this. You got to know these two. Mu naught is 4 pi times 10 to the minus 7 henries per meter. Epsilon naught is equal to 8.854 times 10 to the minus 12. And that's farads per meter. Now, some people like doing it this way. They put 1 over 36 pi times 10 to the minus 9th farads per meter. That's fine. You got to know those. So now turn the crank on your calculators, your computers. If you have, I like MathCAD. There's a free version of it. And I do all my things because it's WYSIWYG. It's what you see is what you get. Not like MATLAB, it's cryptic, right? What do you get for this first one? Give me a magnitude and an angle if you don't mind. Who asked this? Who asked this question? Nobody's going to. You asked it. All right. You don't have a calculator? Work with me on this, guys. I'm trying to help you. Huh? This is not that big of a deal. Come on. Anybody? Hey, you're back there. Don't you have one far back? Yeah, Mountain Dew.
All Barrett
I got a weird number.
Give me eta first, if you don't mind.
How do you?
What do you have?
I got a weird number.
That's a great number. What is it?
0.000132.
Anybody else? At what end? At what end? At what end?
It's a decimal. 0.0019.
It's at 45 degrees. What you do?
I got 1.26 at 45 degrees.
That sounds right. 26 at 45 degrees. That's right. This is a good conductor, so it's going to be at 45 degrees. That sounds right. I can't guarantee. What about gamma? You're going to get alpha the same as beta, but what do you get for that? Give me an idea of it.
4,442.
4,442. All right. So it's 4, 4, 4, 2, 1 plus J, because here alpha is beta, isn't it, class? Right? It's a good conductor. How can you tell it's a good conductor? Anyone? Anyone?
Alpha and beta.
Say again?
Alpha and beta.
Well, yeah, that's an aftermath. But the way you see if it's a good conductor, take a look at sigma and compare it to omega epsilon. Now, sigma in this one is 5,000, right? Just follow me on this. What is omega epsilon? Well, it's omega, right, times 72 times epsilon naught. What is that? Just tell me what this is, and I'll show you why I'm doing what I'm doing. Omega epsilon, what do you get for that?
Oh.
Yeah, punch him.
Are we still punching? I got 4.
Say,
4.
just 4? The number 4? All right, can you all see that sigma is much, much greater than omega epsilon? It's a good conductor. That's why I know it's going to be at 45 degrees. Got me on this, class? All right. Now, what's the next thing we're going to do? We've got 1 plus j times 4, 4, 4, 2, correct? Alpha is the same as beta in this one. Do you all agree? Can you see it back there too? Kind of, sort of?
Just barely. There's like a weird glare.
You know, somebody told me that. I can't do a thing about that. Is it bad on that side of the room or just this side?
It's just the top.
I mean, it's still legible. It's just kind of, you gotta.
Well, let me try something. If I don't know where the glare is coming from, but let me try something. Right? Suppose I.
So, I don't think you're gonna fix it.
What I'm trying to do is not turn that down.
That makes it worse.
I mean, you're gonna have to turn them all off. to
Front
keep running.
one's off, and front one on.
Which ain't gonna help.
Is that what they're trying to all the lights off?
Hold on. What I'm going to do is try to trim down this one. I don't know if I'm going to. Is that up? Can you all see? Is that all right? Great, great. What about the phase velocity? What is it? You got omega, you got betas 4, 4, 4, 2, right? What is it? Do the division. Class?
1.4 times 10 to the 6th.
6 meters per second. You realize that's much, much less than speed of light. The speed of light is 300, right? Times 10 to the 6th. Or 3 times 10 to the 8, correct? So it's much, much less than the speed of light. In a vacuum. What about wavelength? 2 pi over 44442. Anyone? I'm trying to do this for your sake, so you got the numbers.
Excuse me.
Help me. 1.4 millimeters? Thank you. 1.4 millimeters. Anything else in this one? They want H, right? Correct? Now, we can get H, listen to me, on this one. Let's look at this formula right here. I'm going to put it in terms of a phasor over here, and I'll write even larger. I can say the incident E field here is equal to 5e to the minus 4442 times z, right? Times e to the minus j 4442 z ax. Do you all agree with that? Ax. Now, by looking at this, you see a minus beta z. It means it's propagating in the plus z direction. Or you could look at this. There's a j beta z, and you can see it's minus j beta z. It's propagating in the plus z direction, so a unit vector in the direction of propagation is az. Do we all agree with that? Now, once we have that, to get the value of h, and I'll do it right here, h, by using the formula I showed you, the simple one, h, instead of having to do curl of e and then dividing by that constant, really, sigma plus j omega epsilon, dividing that into that to get h, which is a pain, you would have to take curl of e and divide it by minus j omega mu. Instead of doing that, you can use that little trick I showed you, which is 1 over eta, unit vector in the direction of propagation cross v, because these are propagating waves, so you can do that. You can't use this generally. This is for a propagating wave. Are you with me, class? Can you see it back there? Well, what that means, this is going to be 1 over eta. Now notice that has an angle, so it's 1 over 1.26, and it's e to the j pi over 4. I'm going to take it on top, so that means on top I get e to the minus j pi over 4 radians, and I've just taken eta and I put it in. Everybody understand what I've done so far? Give me a show of hands. You see this, guys? All right, now I take that, unit vector in the direction of propagation is az, and I crossed it with e. The e field right there, which is 5 times e to the minus j 4442z in the ax direction. Come up here, and you can see really what happened. I have az crossed ax is ay. The rest is just grouping terms. So my h field is going to be equal to 5 divided by 1.26 e to the minus j pi over 4. And then I have e to the minus j 4442 z in the ay direction. I gotta say one thing about this. You can add these exponents. If you want to put minus j quantity 444z plus pi over 4, you can. But remember that this is in radians. So you want to make sure that is in radians. Got it? Yes?
What was A rho Z?
I'm sorry?
What was A rho Z?
It's the direction of propagation. If you look here, isn't it propagating the plus z direction? That's what AP stands instead of A rho. It's the direction of propagation. Yeah.
So why is it not minus AY when you do Z cross X?
Pardon?
Like in your direction, so when you did your direction of propagation cross AX, why is it not?
Well, AZ is the direction of propagation, right?
Right.
Crossed AX isn't X. I mean,
So why would it not be minus AY though? Or would it
well,
be?
you know, the way you do crosses is this. Normally you put X, Y, and then Z.
Right.
Put arrows here. This way is plus, but if you go this way, it's minus. So we went Z, X, positive Y.
Okay.
Do you remember me? How many had me before showing you this stuff? That's the cross products. They're useful. You have to kind of get a handle on it. And they do that in mathematics courses, don't they? Show you the crossings.
Yeah.
I don't know what they use, but that's what I use.
I mean, I suppose if you're really lost, you can just throw up a matrix and unit vectors.
What's that?
I said, I suppose if you're really lost, you could just do the multiplication or the.
If you're always wondering, because some of these weird, sometimes I get ace and gamma, and they get 5 different unit things they throw on me. They have all these rotated units, so I always put my finger, my index finger, in the direction of the first vector, and just over the short angle go into the second vector. My thumb points in the direction of the cross. Yes.
So for conductors, you said about a good conductor is phase at 45 degrees.
Well, yes, it's going to be for eta. It'll have a phase at 45 degrees, and alpha will be equal to beta. That's the key. Right.
Maybe let's get e to the minus 442.
I'm sorry.
You have e to the minus j 442.
You're right. I don't have the e to the minus the alpha part, 4.44z. I guess I'm trying to go too fast. This should be multiplied in there too, because there's an alpha there. Thank you so much. Follow me, class? There is an alpha in both h and e. If e is decaying, h is decaying, probably anyway. It's that simple. If I seem like I'm trying to move too fast, I got stuff to cover, and I know I can be bugged. Any other questions about that? It's a good question. All right, who tried this one? Somebody did, obviously. All right, you get this basically? Kind of sort. Yeah, that music killer. All right. I had it. Let me tell you, when I was in college, I had a course, and it's advanced mathematics, advanced engineering mathematics. Took it in the summer. Guy teaching it was from Spain, brilliant graduate student. But that guy's English was almost you couldn't understand it. And his writing, you ever had somebody that scripted everything? So I didn't understand what's on the board, and I couldn't understand him. So I was desperate, just reading the book to try to figure out what he was talking about. All right. Are there any big games this weekend besides ours in college football?
Alabama and Duke.
I wish I could say that's a big game, but somehow I'm just not feeling.
Right. We're the only game that's like really no winner.
No, I mean, doesn't Ohio State play like there's got to be one more
I think
conference.
we're the only game for the weekend that's sort of
What's
like-
that?
I think we're the only game for the whole weekend that's sort of
Okay,
like a
I was
touchdown.
hoping, I mean, you had Florida, Miami, Texas.
Yeah.
Well, I got another real, how about Georgia going against, I don't know, Texas A&M? That'd be
I
good.
think A&M and Clemson play week 2.
Who?
Oh, Clemson and A&M will start.
Texas A&M.
Oh, they don't play the week.
They play this weekend?
Next weekend.
Oh, no. All right, back to this. All right, now we're gonna talk about polarization, all right? I wanna cover polarization. I'm gonna tell you at the onset of this, I don't expect you to mathematically know too much about this. Because the real way people, there's so many ways to define polarization properties mathematically. What you have to know is what they mean conceptually. So in general, when we talk about polarization, we're talking about a propagating wave that has an E field in two directions, not just X, but X and Y. So write this down. E in general can be rendered for a propagating wave, and let's do it lossless. There's some E naught X cosine of omega t minus beta z, so it's still propagating in the plus z direction, and this is going to be AX. Then there's going to be a plus E naught Y times cosine of omega t minus beta z. I'm going to leave a little room there. AY. All right, now we take a look at X and Y, and we do something that I love. We allow Z to be 0. You won't see this in books. Allow Z to be 0. If Z is 0, the beta Z goes away. Do y'all follow me on that? Got me on that? That's what, because what I'm about to show you is true no matter anywhere you are in Z, so make Z 0, because that way the beta Z component goes away. Follow me? Now, if you look at this and this and plotted it versus time at Z equals 0, here's X, here's Y, you would see that basically what you get is something where this would be the maximum E naught X, and this would be E naught Y, and there would be symmetric here, and what you have is the tip of this vector, if you look at this, getting longer and longer and longer, hits here, then shorter and shorter, shorter, then it reverses polarity. Do y'all see what I'm doing here? How many see this graph would be this function if you plotted EX there and EY there? Y'all see it? Class, you with me? Now, what do you notice about that? It's a straight line. It doesn't matter if the line's that way, or it's this way or that way. That's called linear polarization. Now, you can write this in terms of phasors. E naught X, e to the minus j beta z, E naught Y, e to the minus j beta z. You see that? That's another way to write it. You can render this thing a million different ways, but that's linear polarization. That's all it means. Usually when they talk about linear polarization, they're either talking about vertical or horizontal. Vertical is where the electric field is in the Y direction or in the up direction here on Earth. Horizontal, it's parallel to the Earth's surface. Either vertical or horizontal polarization. That's the way in radar you talk about things, general antenna engineering. They want to know if your electric field's coming off horizontally or vertically polarized. That's all they want to know, for a lot of different reasons that you'll see in time, the reflection coefficients and other things that depend on. Now, the second one we talk about is circular polarization. With circular polarization, I'll show you what it's doing, then I'll show you mathematically how it's defined. This defines circular polarization. You'll notice this one, the tip of this is basically going, the magnitude of the E field goes to 0 at some point, doesn't it? And then it goes this way, and it's basically modulated up. With circular polarization, you're going to have an electric field strength, E naught, and the only thing that's going to happen is the orientation of that field is going to rotate. Yes, sir?
Did you say it'll always go through 0 or just for this case?
Has to go through 0 for linear polarization. Take a look at that. There's going to be a 0. Isn't there, class? If there isn't, then you won't get this. You'll get something called elliptical. It'll look like this. But I'll get to that. Now, with this, I've got a constant value and it rotates. This is the big thing about circular polarization. I'll give you the math in a second. With circular polarization, the power is a constant, the power density. There is no change in the magnitude of the electric field, therefore the power is a constant. For this one, the power is going to have a peak and a 0, a peak and a 0. Do you follow me? So this is constant power, which is kind of nice for a lot of things in terms of getting power to an antenna and with waveguides that I'll get to later. But there's one other thing about this that's important. With circular polarization, If I send down a right-hand circular polarized wave and it hits the wall, it comes back rotating the other, which means at the receiving end, I can build an antenna that will filter out everything but the polarization I would get from a return. And it's very, very nice for radar work to use circular polarization, and the weather people will actually use elliptical polarization because they can tell a lot about the nature of the storm by how the droplets look. And when you send out an elliptically polarized wave, there's an optimal way to do this. The reflected wave coming back, and that's a little much, but if the larger the actual droplets are, the more they look like a teardrop. And what you get is a stronger vertical return and less horizontal. And they can figure out in a storm cell the relative strength of the storm and by the size of the droplets. And I'll try to get into that later when we do radar. But these are used to interrogate regions of the atmosphere as well as identify targets like aircraft. So mathematically, the way they do this, and there's a lot of ways to. That's why I'm not steeped in the math. There's so many ways to express this. Is they're going to say they have some E naught, all right? And then there's going to be cosine of omega t. Now let's just assume z equals 0, so I won't even put in the beta in there. And this is going to be ax. And then there's going to be plus some E naught cosine of omega t minus or plus, or really plus or minus, 90 degrees. So I'll call it pi over 2, AY. Now, I'm going to assume for now, let's do this. Let's assume it's minus pi over 2. And I'll show you why I'm doing that. Start with omega t equals 0. When omega t equals 0, I get cosine of 0 is 1. So I have E naught AX, right? A cosine of minus pi over 2 is the same thing as cosine pi over 2. It is 0, correct, class? Cosine of plus or minus 90 is 0. So I've got nothing there. So at t equals 0, here's my electric field. That's at t equals 0. You follow me? Now, let omega t be 45 degrees. Just work with me on that. At 45 degrees, I got cosine of 45, which is 1 over square root of 2, times E naught. So really, I've got something a little less. Do you agree with me? But what about the y component? Now I have cosine of, well, that's going to be 45 degrees. We're at 45 minus 90, or cosine of minus 45. Cosine's an even function. Cosine of minus 45 is the same thing as cosine of plus 45. It's 1 over square root of 2, too, right? So now I can see that here on this axis, these two are the same, and I would be here. I can continue on, but you can see that this is rotating in this direction. Can you all see that right there? Like at the hands of a clock, it'll rotate this way. Now the direction of propagation is going to be out of the board. If you think about it, that's X, that's Y, Z's out of the board, and from back here, I made everything propagate in the plus Z direction, right? Now just watch this. If I take my right hand, and I go ahead, and I put it in the direction, my thumb in the direction of propagation, then if I let this thing rotate, like such, right? Rotate this way, that's circular polarization, and that's right-hand circular polarization because my right hand literally is like closing a door. If you put your thumb in the direction that's going, the hands, or my finger on my right hand, if I was acting like I'm opening a door, it's closed, it's going to move this way counterclockwise. Do you follow me? That's right-hand circular polarization. Now, you can guess this. That's right hand, right? What do you think happens if I do this? Take a guess.
Left hand.
Now it would be left hand. Now it would rotate like this. And if I put my left hand in the direction of propagation, it would rotate. I would take your finger and your index finger and let it rotate. It'll go in the your left hand would close the door or open the door. Pardon. You all see that, class? Are you with me on this? Give me a show of hands if you are. And can you write notes back there? You need light. Are you okay with the light back there?
Yeah.
All right. Okay, good. So that's circular polarization. Now, remember, mathematically, a lot of ways to do this. I could write that in a phasor form, couldn't I, class? Right? I can do this a lot of ways. That's why I don't get hung up on the math. Just plot a few points. It tells you what it is, left or right. Just plot basically go at 0 degree, omega t equals 0 and omega t is 45, that's the direction it's going to keep on going forever that way. Follow? It's either going to be left hand or right hand. You all follow me on this, class? And that's why I don't get hung up with these things very much. Anyway, now the next one is going to be elliptical polarization. A lot of ways to define elliptical. Here's the easiest. Take circular and make one of these a different value. I'll call that E naught, and I'll call that, or E naught X, and I'll call that E naught Y, and make E naught X unequal to E naught Y. And now you have elliptical. And the only thing elliptical, this is called elliptical. The only thing with elliptical polarization is this. If this is X and this is Y, now the tip of your field is now tracking an ellipse. And there's a lot of things in the book that say, well, we can figure out the tilt of the ellipse. Not a big deal. I don't care about that. All right? Neither should you. When they do it, that's something that's very specialized when they worry about the tilt and stuff like this. If you're involved with any type of weather radar, you get into that stuff in detail. Because then that can be used for an analysis. If you have an elliptical polarized wave, especially when you can change the orientation of the ellipse in real time, then you can interrogate the atmosphere and really get a good idea of the actual, not just the relative size, but the orientation of the projectiles or of the particles, the rain and stuff like this. And that helps you define the wind shear and the wind speeds and all that other stuff. By the way, one thing I want you to make sure you understand that, has anybody ever seen a water spout? Anybody? It's a tornado over water, right? That's just water then, all right? It doesn't have a large radar signature in general. It has one, but not. On land, what happens is the tornado has a debris field. It sucks in everything, aluminum foil, anything, and it's up there, and that has a much bigger, there's a huge radar signature. Tornadoes on land are much easier to track and define than on water, but water spouts, I never had to interact with these things, but I'm told they're vicious if you're in a small craft and one of them gets near you, that they can really rock your world. And I saw a couple when I was down at the Gulf this year, and I'm thankful I wasn't out there in my boat when they happened. Anyway, just for the record, that's what ellipticals used for a lot, weather radar. All right, next after this, we get into reflection, and I wanted to do oblique incidence. I don't think I can get to it today. Now this is real important, but it's very similar to what you learned already when you had different waveguides basically tied to loads that didn't match their impedance. Or not waveguides, but transmission lines. You had a reflected and a transmitted portion of the voltage and power for that matter. So now we do the reflection of waves, and it's identical in its treatment to that of what you had with transmission lines. So in general, do this. We're going to have region 1, region 2. Region 1 here is going to have some eta 1, and it's going to have some beta 1. It's the only two things you care about. I'm going to make this the z direction. Region 2 is going to have eta 2 and beta 2. Now I'm going to keep the standards that Dr. Wentworth uses. I'm going to say I have an incident electric field here that strikes the surface, some of which is going to be transmitted. In other words, we're going to have an E transmitted. I'm using the small t to indicate transmission. And I'm going to have some of it that's actually reflected. I'm going to have an E reflected. That should make sense. Now, the incident electric field is defined as some E naught incident times e to the minus j. We're going to do lossless. Doing it lossy doesn't really help you in this case. So e to the minus j beta 1 z a x. That's the incident field. Y'all give me that one. That's a wave moving in the right. It's polarized in the x direction. Everybody got that? Then what we're going to do is take E reflected, and it's going to have some E naught reflected, but it's moving in the opposite direction, right? The reflected wave is going away from that encounter right here. So it's e to the plus j beta 1 z a x. And we're also gonna have a transmitted field. And that would be E naught transmitted times e to the minus j. Now it's beta 2 times z ax. Are you all with me on that, class? This is our designations for that. Everybody got that? Now we need the H field. So for starters, you have to get the direction of propagation for each one of these. For the incident and transmitted, the unit vector and the direction of propagation is what, guys? Unit vector, just look. People, come on. AZ direction. Unit vector would be AZ. Do you all agree with that? Are you with me? Can you read this? Stay awake. All right. For the reflected field, what is the unit vector and the direction of propagation? Minus AZ, right? The opposite direction. It's going the other way. Agree, class? Can you all see that back there?
Yes.
All right. Now, to get the H field, what do we do? Well, H incident would be equal to, I'm using the formula 1 over eta, in general, eta 1, A rho crossed into H. That's the general, crossed into E, pardon me. That's the general formula I'm using, 1 over eta, A rho crossed E. Let me just put it this way, make it general. So H incident would be equal to 1 over eta 1. And then I'm going to just tell you what the answer is. It's E naught incident, e to the minus j beta 1 z a z. I'm sorry, yeah, ax, ay, pardon me, ay. When I take E cross H, it's z. Az is the direction of propagation. The E field's in the x direction, so H has to be in the y direction. Ax crossed ay is az. If you don't see it quite yet, think about it after class. It'll make perfect sense. That's positive ay. That's the incident H field. The transmitted H field will be the same form. It'll be E naught transmitted over eta 2, not eta 1, times e to the minus j beta 2 z ay. They're all going to be in the ay direction. But H, this is the one I wanted to do. When I take a look at H reflected, the reflected wave is going to be 1 over eta 1. The unit vector is minus az, correct? It's propagating in the minus direction. You with me? Now I'm going to use this right here. And I cross it into the reflected field, which is E naught reflected e to the plus j beta 1z ax. Now the reason I did this is going to have a negative symbol. If you take a look at this for a second, you see that H reflected will be minus, what's AZ AX crossed AX, class? AY, but we got a minus sign. So it's going to be minus E naught reflected over eta 1 e to the plus j beta 1 z, and it's going to be in the AY direction. Now note that that is a minus sign there. I like to do that. And those are the H fields and the E fields for the region. Now to solve for single coefficients to give me reflection and transmission coefficients, what we do is allow z to be equal to 0, and that's going to be at this interface. Assume at this point right here, z equals 0. So we go at z equals 0, and you'll notice this is the boundary between the two regions, right? Between this. Now there's two laws that are true at that boundary for charge-free and surface current-free. Actually, if they're just surface current-free. H tan 1 is H tan 2. The tangent electric fields across any region of space are the same. And E tan 1 is E tan 2. The tangent, electric fields are the same, the tangent magnetic fields, I should say H tan 1 is H tan 2. Correct, class? So at z equals 0, I say E tan 1 is E tan 2. E tan 1 equals E tan 2. And what that means, E tan 1 is going to be, this is at z equals 0, so it's E naught incident plus E naught reflected is E naught transmitted. Do you all give me that? When you take z equal to 0, what happens to these exponentials? E to the j0 is just 1, isn't it, class? So you just have incident plus reflected equal transmitted at that boundary. There's the first one. When you do H tan 1, H tan 1 is equal to H tan 2. Now the tangent H fields. Well, in region 1, I have the incident and the reflected. So I have E naught incident right? And then I have over eta 1 plus E naught reflected over eta 1 equals E naught transmitted over eta 2. Do you all agree with that? Now that again is equals 0, correct class? Work with me. Now, what I want to do is define a reflection coefficient. This is a reflection coefficient. And the symbol, like it is in back in transmission line theory, is capital gamma. What, are you with me, class? And what that is the ratio of the reflected field to the incident field. Now, how do I do it? Here's how you do it. I'm about out of time, but just listen. See how this is the transmitted field is defined in terms of reflected and incident here, class? Can you all see that? You take this and stick it right here. And when you do, you're going to get E naught incident plus E reflected, E naught reflected, over eta 1 equals E naught. Now I do that one right there. E naught incident plus E naught reflected. Oh. Sorry, this is actually a minus sign, right? There's a minus sign there. I missed that. This is going to be this. So this is going to be actually this. Running out of time. And this is E naught incident plus E naught reflected over eta 2. Just listen to me now. Now, if we go ahead and divide both sides by E naught incident, I get 1 minus the reflection coefficient, 1 plus the reflection coefficient. You all see that? And you will get the reflection coefficient being equal to this. Eta 2 minus eta 1 over eta 2 plus eta 1. That's the reflection coefficient for a normal incident wave. Normal incident means it's coming in directly into the surface. There's no obliqueness to the angle. It's broadsiding. It's striking it solid there. All right? So it's coming in. You could say that it's normal to the surface. Now, hold on for 1 second. I know I'm out of time. There's a transmission coefficient that was 1 plus gamma. Transmission coefficient is 2 times eta 2 over eta 2 plus eta 1. And those are the 2 things you need. I'm going to give you some problems with that. Now, this is very similar to what you did back in the transmission lines class. You won't have trouble with this, but I'm going to give you some problems. Make sure you do it for Friday, all right?